Hey there. Ready to really untangle this web of knowledge.
I like that.
Today's deep dive,
Yeah.
it takes us into the world of network mathematics.
Very cool.
It's kind of like deciphering this hidden language
Yeah.
of connections. And I mean, everything from, how our brains work to the vast expanse of the internet.
Yeah, it really is like holding a magnifying glass up to those invisible threads that tie everything together.
Right.
And we're going to be talking about uncovering those principles that govern how these systems behave, how to predict their future,
Uh-huh.
even reveal those hidden vulnerabilities that make them tick.
Okay, so let's map this out a little bit. I always kind of thought of networks as something visual, like a spider web
Mm.
or a family tree.
Mhm.
But how do we actually translate that into math?
Well, we start by representing those systems as networks, but instead of lines and pictures, we use things called nodes and links. So think of your favorite online social network. Each person is a node. And those connections, the follows or messages, those are the links.
Hmm.
It's a way to simplify complex systems while still capturing their essential relationships.
So like in a transportation network, cities would be the nodes and the roads or flight paths would be the links.
Precisely. And these networks aren't just about who's connected to whom. The nature of those connections matters too. Some links are what we call directed,
Okay.
like a phone call. One person initiates the connection,
Right.
others are undirected.
Right.
Like friendships, they flow both ways.
That makes sense. But most networks in the real world probably have a mix of both, right?
You're absolutely right. Think about the internet.
Okay.
Websites link to each other in a very specific direction,
Uh-huh.
but the physical cables connecting them don't care which way the data flows.
Right.
And in a biological system like a cell, some interactions between molecules are reversible, while others operate in a single direction.
Okay, so we've got our nodes and links and we figured out, which way the connections flow. Now, how do we actually start like crunching the numbers to unlock those hidden patterns?
That's where this thing called the adjacency matrix comes in.
Okay.
It's a really powerful tool that lets us translate the network structure into a mathematical form that we can actually analyze.
Okay.
So imagine a grid where each row and column represents a node in the network. If two nodes are linked, we put a 1 in the corresponding cell.
Uh-huh.
Otherwise, it's a 0.
So it's kind of like a digital blueprint of the network's connections.
It is.
But what insights can we actually glean from this matrix?
Oh, a whole treasure trove.
Okay.
For one, it lets us calculate the degree of a node, and that's simply by counting how many ones are in its corresponding row or column. This tells us how many connections a node has, which can be a proxy for its importance or influence in the network.
So in the network of Hollywood actors, someone like Kevin Bacon with tons of connections would have a very high degree.
Right. Exactly. And the higher the degree, the more likely a node is to be what we call a hub, playing a crucial role in connecting different parts of the network. But degree is just the tip of the iceberg.
Okay.
This matrix allows us to calculate other important metrics, like the shortest path between two nodes,
Uh-huh.
which is crucial for understanding how information or resources flow through the network.
So like figuring out the most efficient route between two cities on a map.
Precisely. We can even use the adjacency matrix to calculate what's called the clustering coefficient, which measures how tightly knit a node's neighbors are.
Okay.
So think about it this way.
I'm picturing like a high school clique where everyone in the group is friends with everyone else.
Yes.
That would be high clustering, right?
Exactly. And high clustering can have significant implications for how information spreads,
Okay.
or how resilient a network is to disruptions.
This is fascinating. So we've got this powerful matrix, but how do real-world networks actually measure up? Are they just random jumbles of connections, or is there a hidden order to the chaos?
That's one of the most intriguing discoveries in network science. Most real-world networks aren't random at all.
Hmm.
They exhibit a fascinating property called scale-free.
Scale-free. What does that even mean in the context of networks?
It means that the network structure is dominated by a few highly connected hubs, while the vast majority of nodes have only a handful of connections.
Okay.
Think of the internet.
Oh?
A few giants like Google and Facebook hold the whole network together.
So it's like a popularity contest where a few superstars attract the lion's share of the connections.
That's a great analogy.
Hmm.
And this scale-free structure isn't just a quirky observation. It has profound implications for how networks behave.
Like what?
For example, they're incredibly robust against random failures.
So like if a bunch of smaller websites crash, the internet as a whole keeps humming along because those giants are still holding it all together?
Exactly. But there's a catch. They can be surprisingly vulnerable to targeted attacks on those hubs. Imagine the chaos if Google went down. The internet would be crippled.
Okay, that's making me sweat a little bit.
Right.
So understanding this vulnerability is crucial for protecting critical infrastructure. Right.
Absolutely. And that's why the study of network robustness is a crucial area of research. We're constantly trying to understand how to design networks that can withstand both random failures and targeted attacks.
It seems like a delicate balancing act.
It is.
But it sounds like we've only just scratched the surface of what network mathematics can reveal about the world. Where do we go from here?
Well, understanding network structure is just the first step. Now we need to delve into how these networks actually behave, how information flows through them, and how they evolve over time. That's where things get really exciting.
Okay, so we've mapped out, the basic structure of networks, but they're not just static blueprints, are they?
Right.
I mean, how do they actually grow and change over time?
That's a fascinating question. One of the key mechanisms driving network growth is something called preferential attachment. It's the idea that new nodes joining the network are more likely to connect to those that already have a lot of links.
So it's kind of like the rich get richer. The more connections a node has, the more attractive it becomes to newcomers.
Precisely. Think about a new website launching. It's more likely to link to established giants like Wikipedia or the New York Times than to another obscure, newly created site. This preferential attachment helps explain why so many real-world networks exhibit that scale-free structure we talked about earlier.
But surely it can't just be about who got there first. I mean, not every website or social media account becomes a massive hub, right?
You're absolutely right. There's another crucial factor at play: fitness.
Okay.
It recognizes that nodes have inherent qualities that make them more or less attractive to connect to. Some websites have more engaging content. Some companies offer better products, and some people are just more charismatic.
So it's not just about being an early bird, it's about having something unique to offer. A certain je ne sais quoi that draws people in.
Exactly. And this fitness adds another layer of complexity to network evolution. Sometimes a node with high fitness can overcome a late start and still become a major hub. Think about how a relatively new social media platform like TikTok exploded in popularity, surpassing those established players.
That's a great example. So it's this interplay of preferential attachment and fitness that shapes the network's destiny.
Precisely. And the specific rules of attraction can vary depending on the network. In some networks, like social networks, we see what's called assortative mixing, where hubs tend to connect to other hubs. Think of those celebrity power couples, popular individuals gravitating towards each other.
Right. But in other networks, we might see disassortative mixing.
Exactly.
Like in an ecosystem, a top predator might avoid connecting with other top predators, preferring to prey on smaller animals lower down the food chain.
Exactly. The dynamics can be incredibly complex, but by understanding these patterns, we can start to predict how networks will evolve and how we can influence their growth.
It's amazing how much insight we can gain from just analyzing these like simple connections. But we've talked a lot about the structure of networks.
Right.
How do we actually study what's happening on them? Like how information spreads or how a virus might travel through a population?
That brings us to the fascinating field of dynamics on networks. We're not just looking at the static map anymore. We're trying to understand the movement and flow across those connections.
So like understanding how a rumor spreads on Twitter or how a traffic jam ripples through a city's road network.
Precisely. And those dynamics are heavily influenced by the network structure. Remember that scale-free property we discussed?
The one where a few hubs dominate the network.
Exactly. That structure can make networks incredibly vulnerable to the rapid spread of things like viruses or misinformation. Imagine a virus infecting a highly connected individual. It can quickly jump to their numerous connections and spread like wildfire.
Okay, that's a bit unsettling, but it highlights how crucial it is to understand these dynamics, right? So how do we actually go about studying them?
One way is by using mathematical models. A classic example is what's called the SAR model, which stands for Susceptible, Infected, Recovered. It helps us simulate how an infectious disease might spread through a population.
SAR model. Sounds a bit like a medieval knight. But seriously, how does it actually work?
Well, you start with a population of individuals, some susceptible, some infected. The model then tracks how the infection spreads based on factors like the probability of transmission and the network structure connecting those individuals.
So we can use this model to run simulations and see how an epidemic might unfold on different types of networks. That seems incredibly useful for public health planning.
Absolutely. And by tweaking the model's parameters, things like the transmission rate or the effectiveness of interventions, we can explore different scenarios and potential strategies for containing an outbreak.
So we can see how things like social distancing or vaccination campaigns might impact the spread of a disease. It's like having a virtual laboratory to test out different public health strategies.
Precisely. And this network approach isn't just limited to epidemiology. We can apply similar models to understand how information spreads on social media, how ideas propagate through a community, or even how financial crises might ripple through global markets.
It's incredible how this network perspective can be applied to so many different fields. It's like a universal language for understanding complex systems.
Yeah.
But as we delve deeper into these dynamics, are there ways to identify the key players in a network?
Yeah.
Those who wield the most influence or control.
That's where the concept of centrality comes in. It's all about pinpointing those nodes that hold the most sway within the network.
So like the social media influencers who can make or break a brand with a single tweet. Or the power brokers in a political system who control the flow of information and resources.
Exactly. But it's not just about popularity. There are different ways to measure centrality, each capturing a different aspect of importance.
Okay, so it's not a one-size-fits-all metric. What are some of these different flavors of centrality?
Well, one we've already touched on is degree centrality, which simply measures the number of connections a node has. The more connections, the higher its degree centrality.
Makes sense, but you said there are other measures.
Right. Another important one is between nodeness centrality. It measures how often a node lies on the shortest path between other nodes in the network.
So it's not just about how many connections you have, but about where those connections are. Like if you're the bridge between two otherwise disconnected groups, you have high betweenness centrality.
Precisely. And nodes with high betweenness centrality can play a crucial role in controlling the flow of information or resources through a network. Think about a busy intersection in a city or a key internet router that connects different parts of the web.
Okay, so those are nodes you definitely don't want to see fail. They're like the linchpins holding the whole system together.
Exactly. And then there's closeness centrality, which measures how close a node is to all other nodes in the network, on average. Think of it as a measure of a node's reach, how quickly and easily it can spread information or influence throughout the network.
So like a node situated right in the heart of the network, with short paths to everywhere.
Precisely. Nodes with high closeness centrality can be incredibly effective at disseminating information or coordinating activity across the network. Think about how quickly a viral tweet can spread from a highly connected account, reaching millions of people in a matter of hours.
This is fascinating. It seems like understanding these different measures of centrality could be incredibly useful for all sorts of applications, from marketing and social media strategy to understanding the dynamics of organizations and even predicting political outcomes.
Absolutely. And as we collect more data and develop more sophisticated tools, our ability to identify and analyze these influential nodes will only continue to grow.
This is truly mind-blowing. It feels like we're starting to see networks everywhere, like hidden threads connecting everything in the universe.
You're starting to see the world through a network lens, and that's exactly what network science is all about. It's a way of thinking that can unlock incredible insights into the complex systems that shape our lives.
Okay, I'm hooked. What other fascinating aspects of networks are waiting to be explored?
Well, one area that I think you'll find particularly intriguing is the study of community structure within networks.
Community structure. So, like identifying the cliques and subgroups within a larger network.
Exactly. You know how in social networks, people tend to cluster together in groups based on shared interests, backgrounds, or beliefs?
Right. Like my book club friends on Goodreads, or the online gaming community I'm part of.
Precisely. And this tendency to form communities isn't just limited to social networks. We see it in biological networks, where proteins might cluster together to perform specific functions, or in ecological networks, where species might group together based on their interactions and dependencies.
Okay, so community structure seems like a pretty intuitive concept. But how do network mathematicians actually go about identifying these communities? It doesn't seem like it would always be clear-cut.
You're right, it can be quite challenging. There's no one-size-fits-all method, but there are a variety of algorithms we can use to detect community structure. These algorithms typically try to find groups of nodes that are more densely connected to each other than they are to the rest of the network.
So they're looking for those clusters where the internal connections are strong and the external connections are weaker, like identifying those tight-knit friend groups within a larger social network or those isolated ecosystems on remote islands.
Exactly. And one of the most popular algorithms for community detection is called the Louvain algorithm.
Louvain algorithm. It sounds almost musical. How does it actually work its magic?
It's an iterative algorithm that starts with each node in its own community. It then tries to move nodes between communities in a way that maximizes something called modularity.
Modularity. That sounds a bit like a measure of how well defined the communities are, like how distinct and well separated those groups are from each other.
You got it. Modularity is a quantitative measure of how well a network is partitioned into communities. The higher the modularity, the more clearly those communities stand out from the background noise of the network.
Okay, so the Louvain algorithm is kind of like a detective, shuffling nodes around until it finds the arrangement that reveals the most distinct and well-defined community structure, those hidden patterns of connection that might not be immediately obvious.
Precisely. And understanding community structure can be incredibly valuable for all sorts of applications. For example, in social network analysis, it can help us identify influential groups, predict the spread of information, or even design more effective marketing campaigns that target specific communities.
And in biological networks, could it help us understand how different proteins work together in clusters to carry out specific functions? Or in ecological networks, how different species form interconnected communities within a larger ecosystem?
Absolutely. Community detection is playing an increasingly important role in fields like systems biology and ecology, helping us make sense of the complex web of interactions that govern life on Earth.
This is truly fascinating stuff. It feels like network science is providing us with a whole new set of tools to understand the world around us.
It is. And as we continue to explore this field, I have no doubt that we'll uncover even more amazing and surprising insights.
Okay, I'm ready to dive deeper. What other wonders await us in the realm of network mathematics?
Well, one area that I think you'll find particularly intriguing is the study of network resilience.
Resilience, like how well a network can withstand shocks and disruptions.
Exactly. In today's interconnected world, networks are constantly facing all sorts of challenges, from random failures to targeted attacks to natural disasters. Understanding how networks respond to these challenges is crucial for designing more robust and resilient systems, from power grids to transportation networks to communication systems.
Okay, so like how well can the internet function if a few key routers go down? Or how quickly can a transportation system recover after a major storm?
Precisely. And it turns out that network structure plays a huge role in determining resilience.
So some networks are just naturally more resilient than others based on how they're wired.
Exactly. And one of the most robust network topologies is something called a mesh network.
Mesh network. Sounds a bit like a chain link fence.
You're on the right track. In a mesh network, each node is connected to multiple other nodes, creating many redundant paths for information or resources to flow through.
Okay, so it's like having multiple backup routes on a map.
Yeah.
If one road is blocked, you can still get to your destination by taking a different route.
Exactly. And mesh networks are used in a variety of applications where robustness is critical, such as wireless communication networks and sensor networks.
So if one sensor in a mesh network fails, the others can still communicate with each other and relay information back to a central hub, like a well-coordinated team where everyone can pick up the slack if one member goes down.
Precisely. And another highly robust network topology is the scale-free network, which we discussed earlier.
Right, the ones with a few highly connected hubs and many less connected nodes. But weren't we saying how those hubs can be points of vulnerability?
You're right, hubs can be vulnerable to targeted attacks. But scale-free networks are incredibly robust to random failures because the vast majority of nodes are those less connected ones, whose removal is unlikely to disrupt the overall network structure.
Okay, so it's like a trade-off between robustness to random failures and vulnerability to targeted attacks. A bit like a fortress that's well protected against a general siege, but might be susceptible to a well-placed strike at its weak point.
Exactly. And one of the key challenges in network science is to understand how to design networks that are robust to both types of threats.
So it's like finding the sweet spot between having enough redundancy to withstand random failures and not having so many hubs that the network becomes too centralized and vulnerable to attacks.
Precisely. And to do this, we need to develop sophisticated mathematical models and algorithms that can assess the robustness of different network topologies and identify potential points of vulnerability.
This is truly fascinating stuff. It feels like network science is giving us a whole new set of tools to navigate the complexities of our interconnected world.
It is. And as we continue to explore this field, I have no doubt that we'll uncover even more amazing and surprising insights.
Well, I'm definitely ready to dive deeper. What other wonders await us in the realm of network mathematics? Okay, I'm sensing a theme here. It seems like a lot of network science boils down to finding that sweet spot between competing forces, like enough hubs to create robustness, but not so many that they become vulnerabilities.
You've hit the nail on the head. It's all about finding that delicate balance, between connectivity and resilience, between efficiency and redundancy. And one of the tools that helps us strike that balance is the study of network controllability.
Network controllability, as in, like, how can we actually influence or manipulate the behavior of a network?
Exactly. Imagine being able to steer a network towards a desired state, whether it's stopping the spread of a disease, optimizing traffic flow, or even nudging public opinion in a certain direction.
Wow, that sounds almost like science fiction. But I guess in a way, we're already doing this all the time, right? With things like advertising and public health campaigns.
You're absolutely right. But network science gives us a more systematic and rigorous way to think about these interventions. It helps us identify those key leverage points in a network, those nodes, that if we can control them, allow us to control the behavior of the entire system.
So it's like finding the puppet masters of the network, the ones who can pull the strings and make everyone dance to their tune.
That's a very vivid analogy. And identifying these driver nodes, as we call them, is a crucial aspect of network controllability. It's not always about finding the most connected nodes, though. Sometimes a less obvious node might be strategically positioned to exert, a disproportionate influence.
So it's like finding those pressure points in acupuncture. A well-placed needle in the right spot can have a cascading effect throughout the whole body. But how do we actually go about identifying these driver nodes in a complex network?
It requires a deep understanding of the network's dynamics, how information or influence flows through those connections. We need to map out those pathways of influence to see which nodes have the biggest impact on the overall system's behavior.
Okay, so it's not just about crunching numbers. It's also about understanding the subtle nuances of how the network actually functions in the real world.
Precisely. And once we've identified those driver nodes, we can then develop strategies to control them. This might involve things like targeted advertising, incentive programs, or even just providing accurate information to counter the spread of misinformation.
So it's about understanding the network's vulnerabilities, but also its potential for positive change. It's like learning to speak the network's language so we can communicate with it and guide it towards a healthier, more resilient state.
That's a beautiful way to put it. And it highlights the power of network science. It's not just about analyzing data. It's about using that knowledge to make a positive impact on the world.
This has been an incredibly enlightening journey. I feel like I've gained a whole new perspective on how networks shape everything around us. But I have a feeling we've only just scratched the surface. What other frontiers are network mathematicians exploring these days?
One area that's particularly relevant to our, data-driven world is the study of network inference.
Network inference. That sounds like something a detective would do. Are we talking about solving network mysteries?
In a way, yes. Network inference is all about using data to uncover the hidden structure of a network. Often, we don't have complete information about a network. We might only have a partial view of the connections, or we might be missing data on some of the nodes.
So it's like trying to piece together a puzzle with some of the pieces missing. How do we fill in those gaps?
That's where network inference techniques come in. We use the data we do have to make educated guesses about the missing pieces. For example, if we see that two people frequently interact on social media, we might infer that there's a strong connection between them, even if we don't have direct evidence of that connection.
So it's about using the visible patterns to deduce the invisible structure, like Sherlock Holmes using footprints and cigar ashes to reconstruct the crime.
Exactly. And network inference techniques are becoming increasingly sophisticated, allowing us to infer not just the presence or absence of connections, but also their strength, directionality, and even the existence of hidden communities.
Wow. So we're not just filling in the blanks. We're actually uncovering those secret relationships and hidden power structures that might be lurking beneath the surface.
Precisely. And this has profound implications for fields like biology, where we might use network inference to reconstruct gene regulatory networks, or social science, where we might use it to understand the spread of misinformation and the formation of echo chambers.
It's incredible how network science can illuminate those dark corners of complex systems. It's like shining a light into the hidden wiring of the universe.
And as we continue to gather more data and develop more powerful algorithms, the potential of network inference is only going to grow.
This deep dive has been truly mind-blowing. We've gone from those basic building blocks of networks to exploring their complex dynamics, their vulnerabilities, their potential for control, and even the art of deciphering their hidden structures.
And what's truly exciting is that this field is still relatively young. There's so much more to discover and explore. Who knows what amazing insights and applications await us in the future of network mathematics?
It's both humbling and exhilarating to realize that we're just at the beginning of this journey. And for you, dear listener, I hope this deep dive has sparked your curiosity, inspired you to see the world through a network lens. Keep exploring, keep questioning, and keep connecting those dots. Until next time, happy networking.